Continuity. Objectives. By the end of this lesson, you should be able to explain what it means to be continuous on a graph, use a three-part definition to show continuity at a point, list the known continuous functions, list the types of discontinuities and their graphical representations, and then finally apply the laws and properties of continuous functions. So what does continuous mean? In everyday speech, continuous means that having no breaks or interruptions. What I was always taught is what a continuous function is essentially this question. Can I draw the graph of this function without ever lifting my pencil? So if you could draw a function without having to pick up your pencil, then that's continuous. There's no breaks, there's nothing that stops you. If you have to stop and then jump up and draw it again, that is not continuous. So let's look at an example. F of x equals sine x. Sine of x would appear to be a continuous function, right? I could draw this pretty easily without picking up my pencil. Following the lines is a different matter. And we know sine graphs keep on going on forever. They never end. They oscillate up and down. So that's an example of a continuous function. But to get a more precise definition, we want to look at whether it's continuous on every point of the function. This graph is continuous on every point, but not all graphs are. If we look at a rational function, it's continuous all the way until we get to the hop here. If we look at a function that has a break in it, piecewise function maybe, right? This part is continuous. This part's continuous. But right here, whatever point that is, it's not continuous. So we gotta talk about how to find continuous at every point of a function, or continuity at a point. So here's the criteria, the three-step definition for criteria for continuity at a point. Suppose fx is defined on an open interval containing x equals c, then f is continuous at x equals c if all three conditions below hold. First, if f of c is defined. So let's talk about what that means. Let's draw a picture to help us illustrate that. So here's my first picture. So now what we're talking about is some function where x equals c. So we're just going to say we have a point here, an x value of c. And we're talking about the open interval. So that means we're going to have a little bit on this side and a little bit on that side. Just our interval there. Let me draw one with numbers so we could get a good example of what it looks like. So 3, and our interval could be like from 2, 1, 2, 3, 4. It's a little interval right there. And the first step says f of c has to be defined. Now remember, what define means that you have a y value for that c. So look, I'm just going to put a point right there. Now my f of c is defined. I have a point right here called f of c. When I plug in x equals c, I get that value. Here, let's just do the point 3, 4. So right now I have my f of and here my f of 3 is defined. Right, there's some value, it's 4. So that's the first set of criteria for continuity at a point. Second step, let the limit as x approaches c of fx exist. So remember, if a limit exists, that means you got to show both sides match. So we must show the limit from the left equals the limit from the right. So I'm going to draw this a couple ways. So on this one, we're just going to draw a nice straight line here. Right, the limit exists. If you look at the limit from the left, coming from this side, you get that point. If you look at the limit from the right, you get that point. So in this case, the limit as x approaches c exists. I'm going to draw a little trick here. So I'm going to draw a line like this. Right? Does the limit exist on that? Yeah, you bet it does, right? The limit from the left equals about 1. The limit from the right, the limit from the left equals about 1. The limit from the right also equals about 1. So my limit exists also. So in both of these cases, the limit exists. Right? In this case, from the left and the right, you get that point, and the left and the right on this case, you get that point. Now here's the final part to make it continuous. The limit as x approaches c of fx equals your value f of c. So basically, 1 and 2 have to match, right? The value you get has to equal the limit. That's what makes it continuous. So step 1 is make sure it has a value, make sure the limit exists, and then finally, to be continuous, those two things have to match. That happens here, right? If you look at this one, this is a continuous function, right? My values match. This is continuous. The limit equals the value. If you look at this one, those values do not match. This is a non-continuous function. Right, so that's why it's so important that that we know the 3 steps, because we have to make sure it's defined, the limit exists, and then finally, that they match, right? In this case, they didn't match, so it's not continuous. I can't draw this without picking up my pencil. And that's the idea. So let's do an example where we verify something's continuous at a point. So this is an example. Is f of x equal to x continuous at the point x equals 3? So we have to check our 3 things, right? Step 1. Does f of 3 exist? Well, all you have to do is plug into the function. F of 3 is equal to x, so I'm just going to get 3. So yeah, it exists. Step 2. Does the limit as x approaches 3 of f of x exist? Now remember, our function here is x. I can just plug it in and do that. Now normally you have to check both sides. You have to check the limit as x approaches 3 from the left, the limit as x approaches 3 from the right. But since it's just a function, I can just plug it in, sub it in. Probably more technically correct. And you get 3. Right? I can also check here if you want to see on the graph. So at 3 from the left, you get 3. From the right, you get 3. So yes, the limit exists. And then finally, does f of 3 equal the limit as x approaches 3 of x? And in both cases I got 3. So yes, that holds also. So f of x is continuous at x equals 3. Right? And that's all it is. You gotta check the 3 things. Sorry about that. You gotta check the 3 things. Check if the value exists. Then check if the limit exists. A lot of times you have to check both sides. In this case, we got lucky. It's an easy function to plug it in. And then finally, you gotta check if those 2 answers match. And you have to write it like this, and then you actually gotta write a little sentence. Since f of x equals x is continuous at x equals 3. Let's move on. Discontinuous at a point. If the function f is not continuous at a point c, we say that f is discontinuous at c, and that c is a point discontinuity of f. Point discontinuity is a very big deal. Informally, a point discontinuity is a break or interruption in the graph. So like we talked about before, if you have a graph that looks, let's say, like this, right, whatever point that is, let's say that's 3, that's a point discontinuity. From our earlier example, right, here, right, again 3 is a point of discontinuity. Right, so that's where our graph was not continuous. At 3, it's not continuous. So you can be continuous, like this graph is continuous everywhere but 3. It's continuous at 1. I could run through the same gamut. It exists, the limit exists, and they match. Right, so this graph is continuous everywhere except for 3. So keep that in mind. You know you can be discontinuous at 1 point. It might still be continuous. Most likely be continuous everywhere else, or other places on the graph. So now let's look at an example of a point of discontinuity when we try to prove it's something continuous. So this example. Is the following piecewise function continuous at x equals 2? F of x equals 5 minus x squared where x is less than 2, and x minus 5 when x is greater than 2. Is f of x continuous at x equals 2? So let's check our 3 things. Alright, so our first thing we check is does the function exist at 2? Does f of 2 exist? So, remember the way piecewise functions work? We're going to plug 2, since we're talking about 2 here, we're going to plug into one that has a line beneath it that's equal to. So we're going to use this function, right, the top part of the function. So f of 2 equals 5 minus 2 squared, which is 5 minus 4, which is 1. So yes, it exists. F of 2 equals 1. So it does exist. Now we got to check the second thing. If you remember, our second thing is, does the limit exist? This is the second thing. Does the limit, that spells m, but as x approaches 2 of x exists? Now, the way you do limits, remember, you got to check both sides. And in this case, you actually have to check both sides. We don't have a straight function. This piecewise function is broken up at 2. So you got to check the limit from the left and the limit from the right. Now the limit from the left, we do have an equation for it. Remember, left is from the left side, also as like the less than side. So this is our limit from the left. We're just going to sub the value in. So we're going to do 5 minus 2 squared, which is 5 minus 4, which is 1. The limit from the right would be on this side, the right side of the graph. Right? This graph looks into this effect. That's a straight line. At 2, when we're less than 2, we're a graph of 5 minus x squared. So that's an upside down parabola up 5. So something to this effect. After 2, we're a straight line of x minus 5, so you go down 5 and up 1 over 1. So something to this effect. Now you can see from the graph it's not continuous, but we're going to continue on. So we're going to take the limit as x approaches 2 from the right. So the right hand side, that graph, we're going to plug it in. 2 minus 5, you get negative 3. These do not match, so the limit does not exist. And I could stop there, right? We failed one of the 3 criteria, right? The 3 criteria. I don't need this anymore. 1, f of the value exists. F of c exists. 2, the limit as x approaches c exists. And then 3, 1 and 2 match. F of c equals the limit as x approaches c. Right? Once one of these 3 criteria fails, you're done. You don't check anymore. If you failed a criteria, if you need all 3 to be continuous, number 2 failed. So f of x is not continuous at x equals 3. Right? And it failed number 2 because the limits from the left side and the right side didn't match. So it means the limit did not exist. Here's a picture of our actual graph, the graph we just did. As you can tell from the picture, right, it's a better one than the crude one I did earlier. And this is not continuous, right? If you try to graph this while picking your pencil, you have to stop right here and hop on to the other side. Right, and right here is where the limit failed. Where the limit from the left, right, then meet the limit from the right. So it's discontinuous at x equals 2. So let's move on. Let's talk about what a continuous function actually is. A continuous function is one that is continuous at every point of its domain. That's the key part, of its domain. We don't care about any values for not in its domain. That's going to come up with one specifically. So no continuous function. The following functions are continuous for every of their domain. So these are all the known ones. So the first known one is a polynomial function. If we know it's a polynomial function, then we automatically know it's continuous. So remember, polynomial function is kind of like this. It's an odd polynomial function, right? So those are continuous on every point of the domain. Next, we have the nth root function. Should put function here also. Right, nth root is kind of like this or like this. Kind of what type of root you're doing. Again, for every point on its domain, it's continuous. Next is a rational function. Now the key part again is on its domain. So a rational function typically looks into this effect. Now on its domain, if you look at the 2 graphs, that's a bad graph. Looks something like this. On its domain, they're continuous. Now there's a point where it's not continuous. In this example, like 1 over x graph, it's not continuous at 0, but the 0 is not in this domain because it's restricted. So on its domain is continuous. You know it's not continuous at 0, but that's on its domain. So if you know it's a rational function, as long as we're not in its as long as we're not in the restricted value, it's continuous. And then the final 3, the trig function, trig and inverse trig. Exponential functions. We always talk about trig, right? Trig graphs like a sine, for example. Again, tan, you can think about, what about tan? But again, on its domain. The values that are missing are not in the domain. And log functions. Exponential functions look like this, by the way. And log functions are its inverse. So those are all six of these are always, if we have one of these functions, we know that they're continuous, as long as it fits their domain. Let's talk about one-sided continuity. So one-sided continuity is just kind of what it sounds like. It's continuous on one side. So if function f is right side continuous from the right at the point x to the domain. In its domain, if the limit as x received from the right equals the value. It is left continuous if the limit from the left equals its value. So like we look at this one here. Right, we're trying to decide if it's left side or right side continuous. It is left side continuous, right? That's where the value is. So this function is left side continuous. And that's all it's saying. If we're talking about a graph where we have something like this, and then something like this, you just figure out where the value is, and that tells you what side we consider is continuous. So this is right side continuous. So that's one-sided limits. Let's move on to types of discontinuity. This is where it gets fun. So, first type of discontinuity is removal of discontinuity. That's where the limit exists, but the limit does not match, like the one we did earlier. This is where the limit exists, and f of x, f of c exists, but it fails part 3. They don't match. The limit does not equal the value. We call this a removable discontinuity. So something like that, you can even not have a value there. So these cannot have a value there. So there we go. Right. So these we call these removable discontinuities because we could fix it very easily. We could just fill the hole in. Just change this equation to make that value there. So these are called removable or point discontinuities. So these fail criteria 3 because if you notice they do have a value. Well, in this case it has a value, and then the limit exists. In this case, they actually fail criteria 1. You don't actually have a value. Infinite discontinuity, just like it says. If you have a graph, and you have a vertical asymptote, that's called an infinite discontinuity. Because there's no way we could hop through these to get to the other side. So this is generally with vertical asymptotes. This also fails criteria 1. Right, there's no value. The limit actually exists in this graph, but there's no value at our point. So if one side or both side limits does not exist or is infinite, then we say it has an infinite discontinuity. And then we have a jump discontinuity. So this one, pretty self-explanatory, it looks like a jump. Right, so if I make this at the hop down, cause a jump discontinuity. This happens with piecewise functions generally. And this one you can tell which one it fails. The limit does not exist. So this one fails criteria 2. Limit does not exist in this case. Right, sometimes you can have a value like we do here. Sometimes you don't have to, but this definitely fails criteria 2. So the limits don't match. We call that a jump discontinuity. And then when we actually use the least, we call it an oscillating discontinuity. So let me get this graph correct. Try to draw a straight line. Sometimes it works, sometimes it doesn't. So an oscillating discontinuity looks kind of like this. You start oscillating. So graph kind of starts getting kind of wild. So on this one, if I pick a point like let's say 3, it's hard to tell at 3 what's going on. Is it 1? Is it -1? It's too hard to tell. It's oscillating up and down. It's oscillating up and down there. So it's too hard to tell if it's what it is. So in this one, the limit again does not exist. So fails criteria 2. So this is we don't use them as much, but it is a discontinuity if it oscillates like that. Oscillates really heavily. Maybe I can draw it more crazy. Anyway, some to that effect. Let's talk about some laws of discontinuity, or continuity actually. most regular limit laws, these kind of follow the same rules. If we know f and g are continuous functions, so we have two continuous functions, we could do stuff with them, so make it continuous. Continuity still holds. So first, if we add them up, so if f is continuous and g is continuous, then when we add them up, that new function is continuous. If we subtract them, that new function is continuous. If we multiply the continuous function by k, that new thing is still continuous. For example, right, sine of x. We know that's a continuous function, we talked about it before. If we multiply that and we get 3 sine of x, it's still continuous. It just has a bigger amp now. Right, so multiply by a constant doesn't change it. If you multiply two continuous functions, you get a continuous function. That's pretty crazy. If you divide them, who would have thought that? Right, you divide them, they're still continuous. Except for one thing I checked, wherever the denominator is equals 0, right, that's on the domain. So it's still continuous everywhere, it's just not in the domain. It's not continuous in the domain. No, it's a little funny wording. Power, if you take a continuous function to a power, it's still a continuous function. If you take the root of a continuous function, it's still a continuous function. So kind of like the limit laws, same concept. If something's continuous and you do these operations with them, they're still continuous. And just like limit laws, continuity composite functions. If you have two continuous functions, you plug one into the other. Then the composite of them, right, f of g of x, is also continuous. And likewise, if you have a continuous function, you find its inverse is also continuous. And we actually have an example of that in our known functions. Natural log and exponents are inverse of each other. Right? These two are inverse of each other. And they're both continuous. So if you have a continuous function, its inverse is also continuous. Limits of continuous compositional functions. If g is continuous at point b, and the limit as x approaches c of fx equals b, the limit of g of f of x equals g, the limit of f of x equals g of b. What's going on? Well, the key thing is this thing in the bottom. So let's look at this. All they're saying is here, if you have this, alright, so they give you the limit as x approaches c of g of f of x. What they're saying is, you can put that limit inside, and now it becomes this guy. Alright, so it's g of the limit of f of x. And then the limit of f of x, we knew that was from right here, we knew it's b, so limit of f is b, so now it's just g of b. So again, all this was saying was, hey, if g is a continuous function, then we know what the limit of f is, and we can just pull the limit inside. So let's do an example. Is tan of natural log of x continuous at x equals 1? So they want to, if this is continuous x equals 1. So normally we go through the 3 steps, right? We're going to go, oh, does f of x exist? Does the limit at f of x exist? X approaches 1 exist? And do they match? So we can see that, that's still a fair way of doing this, but a little shortcut now. We have a combination of functions. Right? We have f of g of x essentially, where f of x is tan of x. G of x would be natural log of x. If you notice, these are both continuous, right? They're part of our known continuous functions. And then we talk about if we have two continuous functions and then we have a composition, those are also that's also continuous. So right away, this is continuous. So that part's true. I just got to make sure it's continuous at x equals 1, right? Is x equal 1 in the domain? So let's plug it in and see if it works. So really all I have to check is this first one, just to make sure we actually have a value that it does fit in the domain, that does make sense. So I have this, tan of natural log of 1. We should all know what natural log of 1 is. This is 0. So you have tan of 0. And again, we got to make sure that's in the domain. That gives us a value. Tan of 0 is just 0. We do that. It's this trig. So yeah, it works. It does, right? We have two continuous functions, so its composition is continuous. These are known continuous functions. And we substituted 1 in to make sure it actually exists. It actually is in the domain, which it is. So yes, this is continuous. Now let's look at some AP style continuous functions problems. So AP style continuity questions. Find the value of k so that f of x is continuous everywhere. So they want us to find k so that it's continuous everywhere. So remember, continuous everywhere is where 1 the value exists. Two, the limit exists. And three, those two equal each other. There we go. Now, with a problem like this, the values can exist as long as there's an equal to sign somewhere. So in both of these, there's an equal to sign, there's an equal to sign, so the limit's going to exist. The value's going to exist. So what we have to worry about is these bottom two here. We want the limit to exist, so we want these two sides to match each other, and then we want to make sure our value equals that. And the easiest way to take care of that is this. We're going to set these two sides equal to each other. So we're going to set 2 equal to x squared plus k. It has to take care of the limit. If we want them also to match, well, it must equal at this like junction point here. So what we do next is we're going to plug in our 0 for x. Right, so we're going to sub each other so the limit matches, and then we're going to sub in 0 for x so that we can figure out, so we can make sure that these two values equal each other, so we can get the final part to work. So here's my equation. Now I have to set 2 equals, sub in 0, so 2 equals k. You can double check if you want, right? So this would be x squared plus 2. Right, does the value exist? Plug in 0, I get 2. Does the limit exist? Well, we kind of force it to happen, but you can plug in 0 both of these, and you get 2 and 2. 0 squared plus 2 is 2. And do they match? Yeah. My value is 2, my limit's 2. So that's all you have to do with these. I like these problems because they're fairly easy, right? All you have to do is set them equal to each other like we did here, and then plug in the critical point in for your x to make sure that the values match. And there you go, solve. This is another one. So same idea here. We got one off there what k is, such that these two things that this function is continuous. So I'm gonna set them equal to each other. And that takes care of the limit. I know there's gonna be a value because there's a 1 here. So step 2, I gotta take care of the limit, so set them equal to each other. And then step 3, make sure the limit equals the value. You sub in your critical point there. So sub that in for 1 on both sides. So we're going to get 1 minus k equals 1 squared plus 2. 1 minus k equals 3. Do a little math. Plus k minus 3 minus 3. Negative 2 equals k. So that's a value of k such that these two things are continuous. Again, if we want, we can double check. So if I did 1, right, does f of 1 exist? Right, we use the one with the equal to sign, which would be x minus 1. So we're going to use that equation. So we're going to use the equation of x minus k. And then we sub in our value. So for x, we're going to plug in 1. And for k, we're going to sub in negative 2. So I get 1 plus 2, which is 3. So that's our value. 2, does the limit exist? Right, so I'm going to check the limit from the left side. That would be the top equation here. So again, x minus negative 2. Which would plug in 1, we get 1 minus 1 plus 2, which is 3, which we already had. The limit as x approaches 1 from the right side, which in this case we use the bottom function. So x squared plus 2, we're going to plug the 1 in, 1 squared plus 2, and you get 3. So the limit equals 3. So the limit equals 3, our value equals 3. So yes, it's continuous because the f of 1 equals the limit as x approaches 1 of x. Alright, so if you want to double check it working, yes, it does work. So if we have one of those problems, all we have to do is set them equal to each other. Right? It's always going to have a value if there's an equal to sign. So don't worry about that. What we do have to worry about is the limit. So you set these two things, set the two top and bottom equal to each other, and then you got to make sure the value works. So then you sub in the value in for the x, and then you solve your k. And that is it.